Good morning, everyone. My name is Marisa Tania.
My name is Barbara Novakova. We were pleased to be closely working with Kinevis during this summer, and we want to introduce you our project AI-powered 3D human pose tracking and analysis.
We see that Tom is here. He is also working with us with Kinofis team. Hi, Tom. And later on, maybe our other team will also join us during presentation. So we are presenting the AI-powered 3D human pose tracking and analysis. In this presentation, we will cover what is the project is about,
We will introduce you our main competitors,
the technologies that we use,
diagram and data flow,
also our demo.
then tell you more about client and server,
After that, we will introduce Graph XR, where we visualize the 3D data,
then tell you more about our progress and timeline.
and also the goal and future application of this project. Let me tell you a little bit about why we are looking at this project in the first place. Whether it's for games, motion analysis in biomechanics, virtual reality development, or medical examination, many applications require that people and their movements be captured digitally in 3D real time. Until now, this was only possible with expensive systems like multiple cameras or by making people wearing a bodysuit with tracking points or tracking devices. This requires a lot of hardware and is clearly not scalable for broad use. So we present an affordable solution to detect 3D poses at 30 frames per second by just using two webcams. With the AI power and combining dual data streams through Socket IO, this open source project offers the possibility of turning smartphones and webcams into a multi-view body tracking system without using any trackers. So no more mocap suits or expensive gears. You don't need also high-tech studios. All you need are your browsers and two simple webcams. So how is it possible, Barbara?
The latest development in using deep learning for human pose estimation has impressive stability, speed, and tolerance to occlusion. This project uses pose detection API, PoseNet, and MoveNet that supports multiple models for running real-time pose estimation by simply estimating where key body joints are. While the acceptable level of accuracy in 2D pose estimation has been already reached, 3D pose estimation still requires more work until more accurate models are produced. Let's introduce important concepts. PoseNet and MooseNet will return a pose object that contains a list of keys. Key point is a part of a person pose that is being estimated, such as the nose, right ear, left knee. It contains both a position and a confidence score. PoseNet and MoveNet both detect 17 key points illustrated in the following diagram. By positioning two webcams pointed at the orthogonal direction, we can combine two 2D poses into a single 3D pose stream.
So Akia Soken is also making a similar multi-webcam full body tracking that is called mocap for all. Akia Research Institute VR Lab team turns phones and webcams into multi-view body tracking system. This company could be our competitor. However, they are offering this paid solution for $100, but ours is free since it's an open source project.
Our client is implemented on Observable HQ that introduces the notebook paradigm to JavaScript projects. For those of you familiar with Jupyter notebooks, this is the equivalent with the JavaScript instead of a Python. TensorFlow, which is an open source platform for machine learning. Server-side platform use Node.js and Socket.io with dependencies of Express. We utilize GraphXR to visualize the 3D data. Now let's look into our architecture diagram for this project. We have two webcams notebooks called Webcam 1 and Webcam 2 that are running on Observable HQ. With PostNet or MoveNet API, we are sending skeleton arrays by Socket.io into our server.
From the two webcam clients, we transfer the array of 2D data via socket.io to our server. The server then sends both data into the third client, from the server to this receiver, another observable HQ notebook. This is when we calculate the X, Y, Z coordinates and also gather the 3D post-skeleton data. By combining the server and clients together, we managed to create the 3D data and visualize them in GraphXR. So we have one server, two clients here for webcam 1 and webcam 2. A third client is the receiver and also 3D visualization. This project is very straightforward. Let us show you how we recorded our data. Recording, and then is recording, server is running, recording, server is running, webcam, 1, 2, 3, go. I'm recording the skeleton. Awesome video. Awesome. I'm gonna kill the webcam. I'm gonna turn off the server. I'm gonna download the stop the recording and download the file. And so 457. So for a more clear understanding on how to run the project components, we also created a tutorial video here for you to watch.
We start by opening receiver notebook, run index.js on terminal, double check that server is listening. Then let's open webcam 1 and toggle both buttons. We can double check the server for incoming data. We need to do the same for webcam 2, but don't forget to toggle both buttons. In the receiver notebook, you can check two webcam streams combined. Now it's the time to turn off both webcam by clicking the button and kill the server as well. Check notebooks for incoming data. And next step is to save by pressing the download CSV button.
To visualize data in 3D, create an account on Kinevis GraphXR. First, make sure to download the Scale Graph and Scaley GraphXR from GitHub. You want to create a new project and click on the project icon at the top left. Go to the extension and pick Graph. Click on the View Attached File if you want to change the CSV data as desired. Next, you want to drag the Scaley GraphXR and release it into the background. With your mouse, you can hold the right-click button to rotate the skeleton as needed. As you can see, we are visualizing all the 17 key points here on the top right of the screen. In GraphXR, you can also go to settings and adjust the visualization by changing the line width or the node size. If you want to escape into a virtual reality world, you can also put on your VR goggles and watch your skeleton there without using the controller.
Get ready to detect yourself with MoveNet API. Please check for the link or scan this QR code on your phone.
We are also pasting the link on the chat if you can find it. So if you can, we invite you to try out our project, the webcam set of our project, and let's get ready to detect your post with MoveNet. I'm gonna give you a few seconds. If you are able to open the link, please let me know and give us a thumbs up so we know when to move forward. Thank you so much, team. Thank you. I see some thumbs up. Perfect. Thank you. Okay. I'm gonna open our webcam here. Perfect. I hope you can see this observable HQ notebook that is published and available for everyone. If you scroll down, can you see the Let's Run webcam part? This is gonna be where we want to run our client. Ready? So first, turn on the webcam and then toggle the reset webcam on and off. This is very important because it takes a while for observable HQ to load the data. After you wait for a few seconds, you can scroll down and see your post detection. So we designed this is for a full body post detection. It will be ideal if you can stand further from your camera and showing your full body from head to toe. However, I'm working from my closet, so I only can show you from half body up. So that's our webcam, yeah. As you can see, this is what we are doing with the webcam client. First, we are collecting sources from the webcam stream, as Andrew demonstrated here. Thank you, Andrew. Then we estimate the post with MoveNet and PostNet. After the model detect the poses, we plot the 17 key points from MoveNet on webcam canvas, as we tried just now. We then emit the data through socket I/O to send them to the server. For analyzing purposes, we also save the data in CSV file and use it later. Allow us to explain briefly about the comparison between PostNet and MoveNet. First, we use PostNet as our detection model. However, PostNet has a lot of missed poses, as you can see here. There are a lot of crossing and disappearing during the skeleton point, as demoed by Barbara on the left. We then managed to switch to PostNet, which is the latest machine learning pre-trained library from TensorFlow that is just issued May this year. With MoveNet model, we were able to improve the performance and accuracy for difficult poses depicted at 30 frames per second on average.
Now let's look into our receiver notebook. In the function calculate data, we first combine two corresponding points from webcam 1 and webcam 2. Then we loop through each key point and first calculate, then store, and later save XYZ coordinates that are necessary for 3D plotting. And also for debugging purposes, we plot the resulting average 2D skeleton as you can see on the screen. During our journey, we encountered several challenges related to implementing our clients. First, we have to get familiar with our tech stack, like most of other groups. Then we have to learn how to stream data to another notebook using Socket.io. And lastly, computation of the 3D figure. We don't know what the stereo imaging system and epipolar geometry are, but we want to make this project happen even with limited math background. Our server represents a relay between webcam and receiver. First, we receive data from webcam streams and forward it to the receiver for further computation and analysis.
In the beginning, we implemented our server in localhost and everything went smoothly. However, when we switched to our VM IP domain to connect the multiple devices, it was catastrophic. It turned out that configuring the network between the client and local server was our biggest challenge, partly because our client running on Observable HQ that was loaded over HTTPS, and our server is on HTTP. So it took us a couple of weeks to implement our server due to networking issues. We also encounter a lot of core errors. Luckily, Professor Lim suggested that we create Let's Encrypt certificate, and that solved our cross-origin resource sharing issue. We also expand our VM capacity because our VM needed a constant reboot in the beginning. Thank you, Tom, for helping us with this. And luckily, we are able to double the CPU and also memory capacity from 979 megabyte to 7.77 gigabyte. After that, everything went smoothly. With working client and server, we managed to combine the two streams in 2D into a 3D skeleton points running at 30 frames per second. Here, our teammate, Nico, is demoing how to visualize our 3D data in GraphXR.
Adding depth Z-dimension into visualization let us to rotate our skeleton points and fill in the gaps and limitations that are missing in 2D plane and make us to create real human life experiences. GraphXR is a browse-based visualization tool that brings unprecedented speed, power, and flexibility to the exploration of data 2D and XCOD. Code for GraphXR is in Grove. Grove is a GraphXR version of Observable HQ, and it's on JavaScript.
So Scaly GraphXR is a graph representation of the skeletal point. Each point is a node, and they are connected using edges. And then scale.growth on our GitHub is a JavaScript code to parse the skeletal data and change the positional data of each to animate the skeleton graph. If you think about it, these are just lines and dots. But when we animate them, these dots and lines manage to capture our denser movement accurately. Maybe in the future, we can go further than connecting skeleton key points and visualize them in a muscular level or creating a 3D avatar.
During our first week, we started like most other groups by getting familiar about the tech stack that is going to be needed for implementation and then started to write SOW.
And then on week 2, we were learning Observable HQ and trying to run Postnet and MoveNet model on this platform.
Third week, we spent by starting with Postnet API, and after week 3, we were able to stream Postnet detection.
By week 4, we managed to combine the two webcam stream in localhost. Then we also create a VM and set up Let's Encrypt certificate to start transitioning from sending data locally to multi-devices.
After the fifth week, we solved course issues and sent data from multiple devices.
On week 6, we had our midterm presentation with all of you, remember? And then during this week, we also managed to access our VM and also store 3D points in CSV file for further analysis.
By week 7, we finished implementing test cases, figured out webcam setup, and the frequency of sending the data.
On week 6, we managed to update from PostNet to MoveNet. And we also went to school for 2 days to record our data live. First with Andrew, and then second with Instagram dancer that we messaged named Cynthia. And we also update our SOW.
9 weeks we spent by publishing the final notebooks, finishing documentation, and creating demo videos and blog posts.
And here we are on week 10, doing final presentation with all of you. During the course of 9 weeks, we managed to complete our project with the Kinevis team.
We were able to finish the first main deliverables of combining 2 different webcam streams and forward it to the third receiver.
We also created a fully functional socket I/O server that can receive and emit merged to webcam data streams.
Reconstructing 3D skeleton key points was achieved as well.
Don't forget the testing. We also created test cases for our Node.js server.
Important part of the deliverables is creating documentation in the form of README, code documentation, and commands.
Luckily, we also accomplished our stretch goals that was stated in this project. We updated the post estimation model from PostNet to MoveNet that improved accuracy. And also,
we achieved to visualize 3D data in GraphicsR.
As requested by Kinevis, we created demo video and blog posts. Since it's an open source project, everything is available online. So you can check our README here for further explanation of the project. On this README, you can also find all our links to go to the open source notebook that is available on Observable HQ. This is our receiver, for example. We open our webcam on yours earlier during the live demo. We also have a YouTube video, so maybe follow us on YouTube. We created the behind the scene video, the tutorial, and also creating the 3D demo and project goal plus future application. Last thing, we are excited that our project will be published on the Kinevis website this Thursday, actually. And we are officially a writer in software engineer area.
For this project implementation, we chose a configuration that minimizes the mathematical computation complexity that is not necessary to have this restriction. For future improvements include experimenting placing the camera in different angles and reconstruct the Z point using epipolar geometry and dealing with the lost frames. The next is improving the stability by using Kalman filter to filter noisy measurements. Then we can also eliminate the step of saving the data and directly connect receiver to GraphicsR. Then also the gesture recognition in the virtual world, recognizing simple natural gestures like push, pull, grab, and drag can be a game changer in interactivity and XR.
So to summarize our presentation, here we present our project goal, summary, and future application in this video.
Welcome to AI-powered 3D human pose tracking and analysis. We present an affordable solution to detect 3D poses by just using 2 webcams. This project uses pose detection API, PoseNet, and MoveNet that support multiple models for running real-time pose estimation by simply estimating where key body joints are. By positioning two webcams pointed at orthogonal directions, we can combine the two 2D poses into a single 3D pose stream. Traditional 3D motion capture systems require a sophisticated setup and are very costly. Hence, the multi-webcam system makes 3D pose capture accessible by many more people. Users can choose to detect their motion with TensorFlow's MoveNet or its older brother, PoseNet. By using both tools, users can notice the MoveNet is more accurate and faster in detecting the 17 key body points compared to PoseNet. The development of the client side is done by Observable HQ. There are 3 clients, webcam 1, webcam 2, and receiver. Data is sent from clients to the server and from the server to the receiver through socket.io. We are building our server-side platform in Node.js. In the virtual reality world, we can play the 3D skeleton from various angles. The future goal for this project is to interact in VR with no controllers nor wearables. By detecting 3D gestures in non-costly ways, we hope to reduce the need for body trackers, hardware usages, computational power, and make 3D interaction in VR more accessible. Full body tracking for skeletal animation allows for more user expression, which can humanize users. There are endless possible use cases, including hand motion interaction with data, video games, and virtual meetings in 3D. Maybe next, you can see yourself in VR as a giant or a miniature, or transform yourself into your favorite character. Welcome.
From the beginning, we were keen to work on this project with the Kinevis team. Because AI movement has so many applications, neither of us know anything about the tech stack. However, we were glad to be challenged outside of our Java comfort zone and work with various additional open source library. This project would not have been possible without the support of the Kinevis team. So we sincerely thank Mr. Wei and also Nico for plotting the 3D skeleton in GraphXR, Tom for helping us with the more robust AWS server, Professor Lim for helping us with the course problem, Alex for the blog post, Cynthia as our model, and the rest of Kinevis team. Once we were able to get up and running, we could see that there was so much more to unpack from the 3D pose detection and its application. All in all, we were excited to learn more about the potential use cases for this type of motion capture in VR and where it can expand from here. Thank you so much for letting us sharing our project with all of you. Let us know if you have any question. Thank you, Tim.
Thank you.
Well, thank you, guys. That was an amazing presentation. So with that, yeah, thank you. Thank you for the sponsors for sponsoring the project. And with that, I open the floor for comments or any question from the team here. No questions? Okay.
I just want to make a comment. They did an amazing job. They overcome a lot of difficulties. It's a not easy task. It's like they mentioned, the connecting different parts and dealing with a lot of unknown constraints.
I do agree. It's connecting different systems to talk to each other is it's very challenging, especially as they move from local machine. I deal with a lot of classes where we move to the cloud, and it's not easy, right? Everybody thinks of local host, my machine, and things like that. Once you move into the cloud, it's very hard, right, to break that mentality. But yeah, the guys did an amazing job. Any other comments or questions? I have a couple of questions, as usual. So with the current project, with more cameras make the 3D skeleton more accurate, or is it a matter of have the minimum number to be 2, but you can incrementally add more.
I believe that the purpose for our project is just to make it as simple as possible and how to make mockup easy for everyone to use. So this is the bare minimum that you need. You need 2 cameras. But of course, in the past, they've done it with so much multiple cameras but it's not the purpose of our project here. But maybe it's possible for the future. What do you think, Mr. Wei?
Indeed, it's multiple camera definitely can improve the precision and accuracy. However, we see such a drastic improvement from postnet to movenet, and we realize that the advanced improvement of AI models is probably give you so the benefit you can get from improving the AI model is astonishing. And in this case, adding a 3rd camera are not likely to improve the result a lot.
Okay, I see. Good. All right, and one last thing, which is not really a question, but a comment here. I do hope that after seeing all the issues and resolutions on the project, you guys are documenting all those very well, right? Like the course issues that you encounter, the SSL, HTTP and things like that, so that anybody trying to use the project have all that information in place.
Yeah, we spent quite a time of preparing the documentation.
Very well, good. So yeah, as you guys have gone through, creating open source is not as easy as it sounds, because it requires a lot of documentation, blogs, as you mentioned there, and providing tutorials, which helps the community, right? Without all that, you might not even get people involved or pay attention to your projects. Okay, with that, thank you, and thank you, Wei, for your project. It was very interesting, and actually I see how the team went through the whole process. Thank you, Tom and Nico, for all your help
Thank
in the
you.
team.